Okay, the recording I forgot to start at the beginning. Anyway, I'll upload this document so you can look at it. Now, this was the rate of change of property of the system which occupies the control volume. Okay. We'll use Reynolds transport theorem in the translating frame. So rate of change of the property of the system inside the moving control volume, one can write as the rate of change, a temporal term, and a flux term. So as I have shown you in detail in previous classes, if I use the del t prime, that is the temporal derivative in the moving frame, then I must use the relative velocity, the velocity of the fluid in the moving frame. The reason we are using this form is that the flow is steady in the translating frame. So del t prime of this flow quantity, rho phi, is 0. But del t is not 0. Now if I use here del t, then I would have the absolute velocity here. But then del t will not be 0, so I have to estimate this term. The advantage of using this form is the first term will be 0, because this is like a definite integral over the region. So therefore, the rate of change of the property of the system is simply the flux of the property through the surface. Now, as you have seen, there is one inlet and two outlets. So W dot N is non-zero only at section 1, section 2, and section 3. Although section 4 is moving, there is no flux of fluid through the section. So on the rest of the surfaces, W dot N is 0. And hence, in a one-dimensional situation, this net efflux of property will have three components. One is the influx, so I have the minus sign here. So W dot N is negative on section 1. So you will have rho phi at section 1 multiplied by this minus W1 A1. And then you have the outflux of the property through section 2 and the outflux through section 3. So I can write it simply as minus M1 dot phi 1 plus M2 dot phi 2 plus M3 dot phi 3. So physical interpretation of these terms is, let us say the last term is the flux of property through section 3. Similarly, the middle term is the flux of property coming out of section 2. And M1 dot phi 1 is the flux of property at section 1. So this is coming in. So the change of the property, if you want the rate of change, it is the outflux minus the influx. So there are two terms, two sections which are outlets. So you have to add these two. So the sum of M2 dot phi 2 and M3 dot phi 3 is the net flux of property coming out of the control volume. And from that, if you subtract the flux of property coming into the control volume, you have the net efflux. So if I take this and substitute into the left-hand side of this equation, which looked like a complicated integral, now we have got an algebraic form for the left-hand side. So there are three terms on the left-hand side and there are three terms on the right-hand side. Then we end up with an equation of this form, which I have numbered equation number 78. So left-hand side here is the net efflux of the total energy through the control volume. Right-hand side has the heat term, and the work term I've written now as minus of PB. So if PB is positive, then energy will be extracted from the fluid. And you have the flow work term, which I've shown you before. Now we want the power developed by a blade, a single blade, which I am calling P subscript B. So rearrange this equation, move this term involving PB to the left hand side of the equation, and throw all these three terms from the left hand side to the right hand side. So after transposing, you have PB is this term, the flow work term. So this group of terms in this parenthesis represents the net flow work done on the system. Okay. And if I move these terms on the left hand side to the right hand side, the signs will change. So we'll have the influx of the property minus the outflux. And I've kept the heat term as it is. So now this phi, of course, has three components. So phi is the sum of internal energy, kinetic energy, point unit mass, and potential energy, point unit mass. So what we can do is substitute the definition of phi, and instead of this middle group of terms, you will have four terms, one involving the internal energy terms, one involving the kinetic energy terms, and one involving the potential energy terms. So you see how we can extract power from the fluid. Well, you have the flow work, the change in the internal energy, the change in the kinetic energy, and the change in the gravitational potential energy, and the heat which is added in. So this is a very general expression, and this actually is a form of your steady flow energy equation. In this case, with one inlet and two outlets. So section 1 is the inlet, and 2 and 3 are the two outlets. Now I've rearranged this. I've kept the change in pressure as the first group of terms, the change in potential energy, gravitational potential energy, as the second group of terms, and the change in the kinetic energy as the third group of terms. And what I've done is I've combined this change in internal energy with the heat added in. And I put a minus sign here. So here you had plus Q dot in. So if I factor out a minus sign, then you'll have minus Q dot in. Okay. And if I factor out a minus sign, then this M2 dot E2 and M3 dot E3 I'll write in the beginning, and then from that I'll subtract minus M1 dot E1. So this minus outside and this minus inside will give you a plus over here. Now there's a very good reason why I factored out the minus sign. If you recall, we have discussed this before for the case of steady flow energy equation with one inlet and one outlet. This entire group of terms you can identify as the head loss. And the other three terms are the three components of the total head: the pressure head, the velocity head, and the elevation head. So the first group of terms in equation number 79 represent the contribution to the work extracted from the fluid, that is the power developed by the blade from change in pressure. Second group of terms is the contribution from the change in gravitational potential energy. The third group of terms is the contribution from the change in kinetic energy. And the fourth group of terms represents a kind of loss of available energy. Now, global conservation of mass tells you that the mass flow rate in is equal to the sum of the mass flow rates through section 2 and section 3. Now, the pressure at section 1, 2, and 3 are the same, and it is equal to atmospheric pressure. So, using equations 80 and 81, you can look at the net flow work. So P1, P2, P3 are the same, so I can factor it out and write outside this parenthesis P atmospheric by rho. And then you will have M1 dot minus M2 dot minus M3 dot. So this will add up to 0 because M1 dot is the sum of M2 dot and M3 dot. So you see that the net flow work is 0. So the contribution to PB, the power developed by a single blade, from the change in pressure is 0. And this is characteristic of impulse turbines. Later on, we'll look at reaction turbines, where this sum of these three terms will not be 0. So there the change in pressure will also contribute to the work that is developed by the turbine. So if the pressure reduces, then you will be able to extract work from the fluid in a reaction turbine. Here, the change in the contribution to PV from the change in pressure turns out to be 0. Now, if you look at the contribution to PV from the change in the gravitational potential energy, that is negligible, because as we have seen, the height of the bucket is small, so the change in the potential energy is very small. And the head loss term would be negligible if the flow is inviscid. In that case, if you come back and look at this equation, the first group of terms we have shown is 0. We can neglect the second group of terms and the third group of terms. So then you can see here that you are able to extract power only by reducing the kinetic energy of the fluid. And this is the absolute kinetic energy. Okay. So we come up with a simple equation that the power developed by a single blade is the kinetic energy flowing into the control volume minus the kinetic energy flowing out of the control volume. Now we need to determine the speed of the liquids. At the inlet, you know V1 is Vj, the absolute velocity of the fluid jet coming out of the nozzle. Now we need to determine V2 and V3, which are the speeds of the liquid at the outlets. We can get it rather easily from once the concept of velocity triangle is clear to you. Now, the buckets are symmetric, so it's easy to show that V3 and V2 will be the same. So in that case, this I'll show you later, but let me use this relation and simplify equation number 83. If V2 and V3 are the same, then I can factor out V2 squared by 2 and write it as the sum M2 plus M3, M2 dot plus M3 dot into V2 squared by 2. And again, this sum of the mass flow rates at the two outlets, if you add it, it's equal to the mass flow rate at the inlet. So if I factor out M1 dot, then you have a simple expression that the power developed by the blade, a single blade, is half M1 dot into V1 square minus V2 square. So you can see that if you want the power to be maximum, that is possible only if V2 is 0. That is the absolute velocity. So if we are able to reduce the absolute velocity to 0, then you will get the maximum power, which in that case will be half M1 dot Vj squared. So power developed by single blade cannot exceed half M1 dot Vj squared. So half Vj squared is the kinetic energy per unit mass available at the exit of the nozzle. To that quantity, if I multiply M1 dot, then you have the maximum power that can be developed by a single blade. Now let us look at the velocity triangles. Okay, we have shown rigorously using the kinematic boundary condition that the relative velocity for an inviscid fluid at any point on the surface of an impermeable solid is tangent to the surface. So if I have a point somewhere here, we will draw the tangent, and the direction of W, the relative velocity will be in the direction of the tangent. So at the outlet also we are assuming that it goes out smoothly. So W2 is tangent to the blade. And to that, if I vectorially add Q, the velocity vector of representing the velocity of translation of the origin of the moving coordinate system, then you have the absolute velocity. So W2 plus U2 is giving you V2. And the angle between minus U and W2 is beta 2 over here. Okay. So as you can see here, if I look at the y component, then the y component of the vector W and V, they are the same. But the x components differ. W to x is larger than V to x by this amount, which is the speed u of the translating vane. So if I want V2 squared, then it is simply V2x squared plus V2y squared, where V2x is the x component of the vector V2 and V2y is the y component. Now the y component V2 is the same as W2 y component, and V2x is W2x minus u. W2x is larger than V2x. So square it and look at this term here, W2x minus u whole square. We will have three terms. One is u square, other is minus 2u W2x. The third quantity is W2x whole square. Now once again, the sum of the last two terms you recognize as W2 whole square. So V2 squared, then the square of the absolute velocity of the fluid at section 2 is u squared minus 2u into W2x. Now again, W2x, the x component I can say is this whole quantity is W2 into cosine of beta 2. And to that you can add W2 squared. Now I can do a similar analysis using the vector triangle at the top over here. So W3 is tangent to the blade. To that you add vectorially u and you get the absolute velocity V3. So the absolute velocity vector is not tangent to the blade. Okay. And you'll have a similar expression, just replace the subscript 2 by subscript 3. So you'll have W3 square here and W3 here. Now we have shown that if the potential energy change is negligible and the fluid is inviscid, then W3 is equal to W2 and both are equal to W1, which is Vj minus U. And if the blade is symmetric, then beta 3 and beta 2 are the same, and I was just referring to it as beta. So equation number 89 and equation number 90 will have the same right hand side. Sorry, equation number 90 and equation number 88. Okay. So I can replace W3 by W2 and keep beta 3 as it is for an unsymmetric blade. But if beta 3 equal to beta 2, then 88 equation right hand side of 88 and 90 are identical. So as we had anticipated, for a symmetric blade, V3 and V2 are the same. Now V1 is Vj, which I can write as U plus W1 because W1 is the relative velocity. W1 by definition is Vj minus U. So V1 squared is equal to Vj squared, which is U plus W1 whole square. So I can write it as the sum of three terms, as I have shown in equation number 94. So what we are interested in is the reduction in the kinetic energy. So if I look at twice the reduction, it is V1 whole square minus V2 whole square. The difference between V1 at section 1 and V2 at section 2. V1 square at section 1 and V2 square at section 2. So I can write it as this group of terms minus this group of terms. So what you observe here is that you have U square in the first group of terms. Okay, here, and you also have U square in the second group of terms. This U square will cancel with this U square. So out of the 6 terms, 2 are cancelling out and you'll be left with 4 terms. So I've written the difference of the relative velocities here, square of W1 and square of W2 here. and I've written in the middle 2u W1 plus, if you have a minus sign here and another minus sign here, this becomes plus. Now, if the fluid is inviscid, then W1 will be equal to W2. So these two terms will also cancel out. So out of the 6 terms, only 2 will survive. And if I use the fact that W2 is W1 and factor it out, then you see that V1 square minus V2 square is twice U W1 into 1 plus cosine of beta. So half of this V1 square minus V2 square, which is the change in the kinetic energy per unit mass, then I can write as U times W1 into 1 plus cos beta. The half and the 2 will cancel out, and in place of W1, I can write Vj minus U. So you can see that the power developed by single blade, which from the first law of thermodynamics we could write as half of m1 dot into v1 square minus v2 square, is then m1 dot into capital U into Vj minus capital U into 1 plus cos beta. And you can compare this expression with the one we had obtained using balance of linear momentum, which again I have done in 2 ways by using 2 different control volumes. And you see that they are identical. But now this analysis using the first law of thermodynamics is giving you a physical feel about the energy conversion. You see that you're getting the power by reducing the absolute kinetic energy of the liquid jet. Okay. Now, as I said before, this square of a real number here, as you can see, is positive, and this also positive. And since you're subtracting a positive number from this, the power you get out will be less or equal to half m1 dot v1 square, and v1 is Vj. So the maximum power you can get in a well-designed front-end wheel by making the absolute velocity v2 0. Now go back to this figure and tell me when v2 can be 0. Anyone? Well, suppose beta 2 is 0. Okay. If beta 2 is 0, then v2y will be 0. Okay. And if w2 is equal to u, okay, then this triangle will collapse into a straight line. So if beta 2 is 0 and u is equal to w2, then v2 will be 0. When will that happen? Well, w2 is the same as w1. So if I say that w2 is u, then Vj must be u plus u, which is 2u. That means if u is Vj by 2, then you'll see that v2 vector will be 0 in case beta 2 is 0. Okay. So you have an upper bound on the energy conversion. That is the maximum PB that you can get is half m1 dot into Vj squared. The actual thing that you get, due to the constraint that beta 2 cannot be 0, okay, is going to be less than that. Now let us see what would happen if you account for viscous forces at the blade. When the fluid is inviscid, or rather the flow is inviscid, we have seen that the magnitude of the velocity of the liquid relative to the bucket doesn't vary along the surface. But in reality, it will be less because viscous forces will slow it down. So we can say that at the outlet W2 and W3 is some factor, a dimensionless constant, which I'm calling the blade friction factor, C with a subscript B into W1. And if I say the fluid is inviscid, then Cb will be 1. So W2, W3, W1 will be the same as we have seen by applying Bernoulli's equation in the more translating frame. But you can put in an empirical factor Cb to get a better approximation and say that W2 and W3 is Cb times W1, where Cb is slightly less than 1. So if we include this, we can modify the momentum balance. Now the momentum balance we have seen before, the net efflux of momentum is what I have over here at the top. Only thing is, instead of W2 now, I'll put Cb times W1. And instead of W3, I'll have Cb times W1. And then we'll end up with a expression where you have, instead of 1 plus cos beta, you'll have 1 plus Cb times cos beta. So the external force which is required to keep the blade from accelerating will be then given by a slightly modified expression, the mass flow rate into the control volume, which is rho times Q1. I put a subscript rho to distinguish Q from the heat into Vj minus U into 1 plus Cb cos beta. So then the power developed by the blade, a single blade, will be of this form. So if I put Cb equal to 1, then this reduces to the analysis that we have, expression which we have derived before. So this is not a very important part of this course. However, I thought I should include it because some of the duality students might be appearing in GATE next February. And there will be a section involving this fluid machinery in GATE. So you should become familiar with this empirical factors also, just in case you're appearing in GATE and you're given a problem where the value of the blade friction factor is given, and then you may wonder what it is. So now let us look at the power developed by the Pelton wheel. So as we have seen, the volume flow rate of water which is issuing from the nozzle is simply the jet velocity into the area of the nozzle. The jet area and the jet velocity, the speed of the water jet. But the volume flow rate of water entering the control volume is not the same. It is, the area is the same, the jet area, and this is the relative velocity, which is Vj minus capital U, which is the speed of the translating control volume. So this is what we are calling Q1, the volume flow rate entering section 1. Because the control volume is moving, the volume flow rate entering section 1 is the relative velocity. So if I compare equation number 105 with equation number 104, you'll see that Q1 is less than Q flow. And the power developed by a single blade involves Q1. Okay. Now, it's customary to assume that all of the liquid which is coming out of the jet will strike one or other of the blades. The wheel has many buckets or blades or vanes, whatever you call it. And the water that is coming out of the jet will strike more than one bucket. So if you have a Pelton wheel or Pelton turbine where the buckets keep entering the jet and going out of the jet, and if all of the flow is captured by one or other of the bucket, then the total, what you might call time average power delivered by the fluid to the rotor of the turbine, which is usually called runner, will be given by an expression similar to 107, but in place of Q1, you will have the total flow Q. Okay. So look at any undergraduate fluid mechanics textbook. They'll have a chapter on fluid machinery, and the power developed by the Pelton turbine or Pelton wheel will be given by an expression in those books which is of this form. Okay. Some of the authors do not give the justification. Okay. So when you do a rigorous analysis for a single blade, you see it is Q1. Okay. But they'll simply write the total flow rate here. So this is making the assumption that the liquid coming out of the jet will strike more than one blade. And the entire flow coming out of the jet is captured by the buckets. Okay. So after a kind of averaging over the cycle, this is an expression which is more near reality. Okay, these are all models. We have made so many assumptions, one-dimensional assumptions, inviscid flow, and so on. Okay. Now, as we have discussed before, if U is 0, then the power is 0. So I put P with a subscript runner for the power developed by the runner. And here I have the total flow rate, which is AJ Vj, not AJ into Vj minus U. So the final expression is rather easy. Okay. If you want to do calculations. Now, when U is equal to Vj, again the power is 0. So the first case, the power is 0 because the blade is not moving. So the point of application of the force is not moving. You will have to apply a force to keep U equal to 0. Okay. But if U is 0, no work is done. Now when U is Vj, the fluid is not striking the blade. So if I go back and look at this figure or the one before, if the control volume is moving to the right with the velocity Vj, then fluid particles will not enter the control volume. The relative velocity will be 0. Okay. So in that case, again, the power is 0. And of course, the blade velocity cannot exceed Vj. So in practice, the blade velocity will be less than Vj. All right, now look at this expression. And let us say that Q is a parameter which you can vary. Beta is fixed for a given symmetric blade. The blade angles are fixed, so you cannot play with this. Once you manufacture a blade, beta is fixed. The density rho here is the density of water. That is also fixed. And let us say the volume flow rate is kept fixed. That means Vj is also fixed, but you can vary U. So by varying U, you can get different values to the power. So when will you get the maximum power? Here. So this is a quadratic in U. Anyone?
When U is equal to Vj by 2.
Okay, so power of the runner is maximum when U is Vj by 2. That means 2U is Vj. Okay. So if 2U is Vj and beta is 0, then you will have the V2 equal to 0, as we discussed before. So what is the maximum power? You just substitute Vj by 2 in this expression. So we'll have Vj by 2, and this also will become Vj minus Vj by 2, which is another Vj by 2. Okay. So maximum possible power is what we have. From this simple analysis, the prediction is given by equation number 110. Okay. Now let me introduce another term which is called hydraulic power. This is the power delivered by the fluid, which is of course water, to the runner. So P hydraulic and P runner, they mean the same quantity. These are different terms. So hydraulic power is given by the same expression, rho times Q flow, which is the mass flow rate of the water coming out of the nozzle, into this quadratic function of U, U times Vj minus U, into 1 plus cos beta. And if you want to account empirically for the viscous forces, then it is 1 plus Cb times cos beta. Now, the energy which is arriving at the wheel is in the form of the kinetic energy of the jet. So you can define a wheel efficiency, which is the power developed by the runner or delivered to the runner, by half m dot Vj square. Now, as we have argued before, this is the maximum possible power that you can get out of the jet. And for a well-designed belt and wheel, if I say the fluid is an inviscid fluid, then V2 will be 0, and you will have half Vj square into m dot. Now, instead of P runner, I can put P hydraulic, and instead of m dot, I can put rho q. Okay. So I have the wheel efficiency. So this is the efficiency of energy conversion. You are converting the kinetic energy of the jet to power of the wheel. Okay. So if I take this expression and substitute over here, the rho q will cancel out, and the half will go as 2 in the numerator, and you will have this u into Vj minus u divided by Vj square, and this factor will remain as it is. Okay. So we'll end up with something like this. I can write it as u by Vj into 1 minus u by Vj multiplied by 2 into 1 plus Cv cos beta. Okay. And let us see what this expression reduces to when at the optimum point, which gives the maximum power. If I put u by Vj equal to half, 2 into half will give you 1, and 1 minus half will give you half. So you will have half into 1 plus Cv cos beta. Now let us assume the fluid to be an inviscid fluid, then Cv is 1. Okay. And then if beta is 0, then cos 0 is 1, and you will have 1 plus 1 by 2. So the wheel efficiency will be 1 in the case, in this very special case, when the fluid is inviscid and beta is 0. In that case, all of the kinetic energy of the liquid will be converted to kinetic energy of the rotor. But in practice, it will be less than 1. So I'll stop here today because it's almost 5. Professor P.K. Das will take the class from 5 to 6. So you have to join the other meeting. We have a couple of minutes perhaps if you have any queries. If not, I'll quickly review what we have done today and move on in the next class.
Sir, here
Yeah.
we are saying this optimum point as like this Vj by 2, u equals to Vj by 2. But this u is not in our hands now. This u will be decided by this flow rate of and this beta.
Yeah. When beta is not equal to 0, the maximum efficiency will be less than 1. Even if the flow is inviscid, it will be half into 1 plus cos beta. See, you can try and find, suppose I say u by Vj is a non-dimensional parameter. Okay. Then the eta wheel, which is of course a non-dimensional, is a function of this parameter u by Vj. So when will u by Vj, for what value of u by Vj will the efficiency be maximum? You can find it directly from equation 115. This also is a quadratic in u by Vj. The efficiency is 0 when u by Vj is 0 and when u by Vj is 1. So if I plot eta wheel versus u by Vj, it will increase from 0 and come back to 0. And there will be a peak at u by Vj equal to half.
Okay, sir.
So that is why I called it optimum point. Okay, I'm stopping the recording. Any other queries?